In this video, we are going to focus on one step in the 8-step hypothesis testing guide process. And that one step is finding a p-value. As you can see in the problem, we're given some information and we're ultimately asked to report the p-value. So the p-value is the area that belongs to the test statistic boundary. The test statistic boundary is found usually using a formula and calculating it. It's where you take your sample statistic and you turn it into a standardized value that you can compare with the critical values. So essentially a z-score formula or a t-score formula if you're doing a claim about a mean where sigma is unknown. So assuming that that's already been carried out, we have a test statistic. This is the z-score version of our sample mean, and we want to see if it is extreme enough to warrant rejection of the null hypothesis. So we're going to put it onto our curve sketch and then find the probability of getting something that extreme or more extreme. And if that probability is very small, then we will reject the null hypothesis. So it's very important, this p-value. So let's do a little sketching first. We have a right-tailed test in this example, and the right-tailed test has a z-score sample statistic turned into a z-score of 2.79, somewhere down in here. And if I draw a boundary up to the curve and then shade the tail, this would be my p-value. So we're just looking for that right area there. So how will we do this? We're going to put in our z boundary of 2.79, and we're going to use that to find the p-value area. And we can use the normal distribution or the normal cumulative distribution function norm.dist and put in the boundary of the test statistic, which is a z-score, so we will use the mean of 0 and the standard deviation of 1. Oh, I forgot to tell it to do cumulative. It always wants to know, should I do cumulative? Yes. 1 for yes. Okay, so this is the area in the left. I could put it like this. The left area, that's why it's so large. So my actual p-value would be 1 minus this, the tiny area in the right tail. So to 4 decimal places, that is 0.00264. Another way you could accomplish this is to, and I don't know why I didn't round it to 4 decimal places, but it still took it. I guess it's just because if you don't round it to 4 decimal places, you might round it and have it be too different from what the answer should be. So like a tolerance issue. Okay, so anyways, I was saying we have the p-value. We just found a certain way, but there's another way too. You can use the negative version of that value to find the twin area on the opposite side. And so if I did norm.dist with the negative test statistic with a mean of 0, standard deviation of 1, 1 for cumulative, then I would have gotten that same answer, right? Because it's just the area under the curve. They are the same on each side. So that's that. Let's look at another version. Okay, so look here. We are now performing a right-tailed, still right-tailed, t-test. Okay, so this must have been a claim about a mean where sigma was unknown. So now instead of having a t-score as my test statistic, I'm going to have a did I say that backwards? Instead of having a z-score, I'm going to have a t-score. So I've been given the t-score of 1.67. And it says it says, do you fail to reject the null hypothesis or reject the null hypothesis? Another way of thinking of this is saying find that p-value again. So my p-value will tell me if I should reject the null hypothesis because it's an area that I can compare with another area called the significance level. And if my p-value is less than the significance level, I will reject the null hypothesis. So the given area of 0.005 for my significance level is going to be my comparison. So I need to get something smaller than that in order to reject the null hypothesis. So let's find the p-value using the given test statistic, and we will do that using not norm this time. That would be if it was a z-score. We're going to use t.dist. So we're under the student's t-distribution, which is also bell curved, but it's just a little wider in the tails. It has more area under the tails. So our boundary is the z-score, and I'm going to go ahead and make that negative so that I can just find the twin area for that. And instead of putting in a mean and a standard deviation, we put in the degrees of freedom, which is n minus 1. Here n was a sample size of 27, so my degrees of freedom is 26. You entered too few more. Oh, I forgot to say, it wants me to say whether I want cumulative or not, and I certainly do. I want cumulative every time. So here is my p-value, and that is not smaller than my significance level, so we will fail to reject the null hypothesis. Let's do another example. You are performing a left-tailed t-test with test statistic t equals negative 0.19 and a sample size of 22. Find the p-value to 4 decimal places. So this time we have a left-tailed test, a given t test statistic of negative 0.19. So negative 0.19. So that's my t-score. My p-value would be norm.dist to the left of this negative test statistic with a mean. Oh, I shouldn't have used norm.dist. I should have used t.dist. It's a t-score. So the t-value, the degrees of freedom, I have a sample of size 22, so I have 21 degrees of freedom here. And always say cumulative. I keep forgetting that for some reason. Okay, now to 4 decimal places, that's 0.4256. So there you go. Okay, and I'd still like us to do another example. Let's do another z-score one. We haven't seen a two-tailed test yet, so let's find one of those. We've done right, we've done left, we've done t, we've done z. Now let's do a two-tailed test, and that could be for z or t. We'll do z-score for this one, as it's given here that our test statistic is negative 2.6. Go ahead and put that in, negative 2.6, and my value is a z-score, so I'm going to use the normal cumulative distribution function rather than the t cumulative distribution function, so norm.dist rather than t.dist. And this is a two-tailed test, so let's do a little sketching action here so we can understand what we're trying to do, what we're looking for. Make sure that our answer is right because it can be a little tricky. All right, so here we go. We have a test statistic of negative 2.6. And so that is on the lower side that would have been a sample mean that started out as a value that was less than the mean and the same scale as the mean. So we will put it way over here, negative 2.6, and we're going to shade to the left into the tail. So from here, this would be our p-value if it was a single-tailed test. However, this is a two-tailed test. That means that you have to imagine that there was a second twin test statistic, even though technically there really is only one test statistic. I mean, you had a sample mean. It was either below the mean, population mean, or above the population mean. And clearly in this example, the sample statistic, the sample mean, was below the population mean, mu, right? So you don't really have two test statistics, but you can think of it that way because that will help you to understand why your p-value is only going to be half over here, and you have to double that up to get the total for a two-tailed test. So back on the spreadsheet, we can use, we'll say, p-value half. Oops, gotta type it right. P-value over 2. That would be norm.dist for my negative z-score with a mean of 0, standard deviation of 1, 1 for cumulative. And that's only half of it, so we need to take it and multiply it times 2, and that'll give us our final answer. And we are done. So that was enough examples of this type of problem.